Okay, so I'm doing a new, like we're continuing from the first recording from section 3.3. We're talking about independence of path, and we're working in a gravitational field. So let me do this again here, and hopefully I won't have any. Here's A. Here's B. Okay, so this path here, this path, hold on. Okay, so like this path here, if it's a gravitational field, the work that the gravitational field does in moving the particle from A to B is negative, because gravity is working against the movement of that particle going up. Okay, so work is negative. Now let me draw another path. Okay, from points A to B, same points, and let's say the path does this. Okay, here's my path. Okay, and this first picture is my C1 path. This is C2 path. Okay, so, all right, let's talk about the work that the gravitational field does in moving the particle from A to B. Let me ask you, would the work overall be positive or negative? I'm talking now for this second picture here. We're done with the first picture. For the second picture, where the path C2 is the overall work that the gravity does in moving the particle from A to B, positive or negative? It's overall negative. That's right. Because from here to here, the work is negative, right? But and let me ask you, from this point here to this point here, is there more negative work being done than was done in the first picture with the C1 path? Yeah, more negative work, definitely. That's right, because you went up higher. You went up higher. But look what happens. To get to point B, I have to go from this point then to point B. And along this part of the path is the work that the gravity is doing, positive or negative? It's positive. That's right, Ryan. So this is positive work, okay, because the particle is going downward and gravity helps the particle. So you have negative work and positive work in the second picture, okay, based on the gravitational field. And in the first picture, the entire work is negative. So we have work 1 here equaling some value, some negative value, and work 2 in the second picture equaling some negative value. Does work 1 equal work 2? Does work 1 equal work 2? It does. That's right, Robin. That's right, Ryan. It does. And that's because the path that you take from point A to point B is irrelevant in regards to the work that the gravitational field does in moving that particle from A to B. Because the gravitational field, it turns out, is a conservative vector field. It is a conservative vector field. Okay, it is a conservative vector field, and if we look in the book here, and that's not the book, obviously, hang on. If we look in the book, okay, back in I can actually go back here, hold on. Now this then, you know, back in section 13.1, at the end of that section, they show that this function f of x of y z equals little m times big M times g, you know, 2 masses, gravitational constant, divided by the square root of x squared plus y squared plus z squared. If you take the gradient of that function, it will equal the vector field that it will equal, all right, hold on. Yeah, I want things to show up nice. If you take the gradient of this function here, okay, if you take the gradient of that function here, and we are you know, looking here at example 1, if you take the gradient of that vector field, then that gradient will equal the vector field f given by that expression. And that's why gravitational field is a conservative vector field. Okay, so I think it was nice just to kind of, how many found it helpful, just the whiteboard presentation of what conservative vector field means? Was that helpful? As an example of a conservative vector field. Okay, John liked it. Okay, wonderful, wonderful. Okay, so it is clear that, you know, some of our most important vector fields in life are conservative vector fields. You know, thank goodness, right? Gravitational field is an example of that. Now, the question is, how, if I want to, how do I know, how can I determine if a vector field is conservative? Well, of course, if you have a conservative vector field, that means, as a reminder, for a conservative vector field, you have to find a function f such that the gradient of that function equals the vector field. But that can take some work to do, and you don't normally want to do that kind of work unless you know first if you have a conservative vector field. Well, there are some theorems that will help us determine that. So in this section here, we talked about independence of path. Okay. In this section, they have a theorem. Well, actually, they ask the question right here. Okay, they ask this question. The question remains, how is it possible to determine whether or not a vector field f is conservative? Okay, well, if a vector field is conservative, there's a condition on P and Q that we can use. So if there's a function f such that the vector field f equals the gradient of f, the gradient of the function f. That means then, if you equate the components, then the vector field f equals p times I plus q times j. So if you equate the components between the vector field f and the gradient vector, p has to equal the partial derivative of f with respect to x, and q has to equal the partial derivative of q with respect to y. Well, what we can do by Clairaut's theorem is, what if we were to take the partial derivative of p with respect to y? That would equal the second partial derivative of f. Well, it would equal that second mixed partial of f with the partial derivative of p with respect to y would equal that second mixed partial. No, it would equal the mixed partial. The partial derivative of f, second partial derivative of f with respect to x, then y. The partial derivative of q with respect to x on the right-hand side would equal the second partial derivative of f with respect to y and then x. But by Clairaut's theorem, those mixed partial derivatives are equal. So that means if you have a conservative vector field, the following theorem has to be true. Okay, the following theorem has to be true. The partial derivative of p with respect to y, remember the vector field f, now this is for a two-dimensional vector field. The vector field f equals p times I plus q times j. If the vector field f is a conservative vector field, then the partial derivative of p with respect to y would equal the partial derivative of q with respect to x. Okay, and that's the condition. That's the condition. And they restate it in a different way here. They restate it, but there it is. If that condition is satisfied, if those partial derivatives are equal to each other, then you have a conservative vector field. Okay? So like for example, in example 2 here, they want you to determine if this vector field is conservative. Okay, is that vector field conservative? Well, P and Q are defined accordingly. P equals x minus y. That's the first component, the I component of vector field f. And Q is equal to x minus 2. That's the J component of vector field f. Okay, well, it turns out that the partial derivative of P with respect to y equals -1, and the partial derivative of Q with respect to x equals +1. Therefore, this vector field is not conservative. Okay, it's not conservative. So that means if you're going to compute the work that vector field does in moving a particle from one point to another point in the xy plane, you would have to work out the integral like you did in section 13.2, and the parameterization would be needed for the particle as well. Okay. On the other hand, in example, well, are there any questions on that? All right, if not, let's go to example 3. Example 3, they want you to determine whether or not this vector field is conservative. And for this vector field, they establish that the partial derivative of P with respect to y is equal to the partial derivative of Q with respect to x. And so you have there a conservative vector field. And actually what they've done is they have a picture here of that vector field. They have a picture of that vector field in figure 9. So figure 8 was the vector field for the example 2, but figure 9 is the vector field for example 3, where we had a conservative vector field. And what they're saying is, if you move along any closed path in the field, the work will equal 0, because the field helps the particle move along the path on some parts and hurts the particle moving along the path in the other parts. But the net sum is equal to 0 for the work. Okay, are there any questions on this? Okay, let's go ahead now and do a few examples here. One moment. Okay. So let me give you a moment to copy this example down. Okay. I want to do 2 examples. I think it would be good to get the examples done, because then that'll help you with section 13.3. So let me let you copy this example down. Okay. So in this problem, we want to find the work done by this force field in moving a particle along the curve C given by this path. Okay, so the path, it's exponential, the components are exponential functions times trig functions, so that would be an interesting looking path. All right, so what might we want to know about our force field? What might we want to know, class, about that force field? Is the force field, I'll give you a hint, conservative? All right, is the force field conservative? All right, well then let's see. Let's see. So of course I could use the, if I mean, what I want to do, right, is I want to compute this integral. And that's the work. That's defined as the work. And of course I could use section 13.2 to what I learned in that section to compute that integral. I do have the parameterization from the particle, but I'm thinking these particular functions might make it somewhat complicated. It might make it hard to compute the integral. So I want to see if perhaps this vector field is conservative. So we'll go here, and it turns out it is conservative. And I think that was actually one of the examples. Is that one of the examples? Yeah, that actually goes with example 3, the fact that this vector field is conservative. But let me give you a moment to, we identify what components P and Q are, and then the partial derivative of P with respect to Y, it turns out equals the partial derivative of Q with respect to X. Therefore, we have a conservative vector field. Okay. Okay, so now what we want to do, is we want to find a function such that the gradient of that function equals the vector field. Okay. All right, I want to do that because I'm going to use the fundamental theorem of line integrals to help me find the work. And to do that, I need to figure out what function f is, what that function f is, so that the gradient of the function is equal to the vector field. That's the key. So, well, we have to start somewhere, right? So again, and we're looking for what's called the potential function. How many have heard of potential function in maybe one of their other classes, an engineering or physics class? How many have heard of a potential, like an electric potential function? Okay, Christopher's heard of it. Okay, very good, very good. So the key is this. We want the gradient of this function to equal the vector field. If that's true, what's the gradient of a function equal to? The gradient of the function is the vector of its partial derivatives. Well, we're saying that the partial derivatives have to equal the components of the vector field. And this is how we arrive at equations 1 and 2. Okay. Please let me know if you have any questions. All right, are we ready to move to the next page? All right. All right. So what I've done to make our lives a little bit easier for us is I've copied these equations 1 and 2 down. I've copied them down. So here they are again. And just let me know, I hope I'm pacing myself well, class. Let me know if I'm going too fast. All right, so what I'm going to do, again, what am I interested in? I want to know what my function of x and y is. What is that function equal to? So, well, what I can do is, since I have a partial derivative of f with respect to x, if I integrate that first equation, that'll, with respect to x, if I integrate the partial derivative of the function with respect to x, if I integrate that derivative with respect to x, that's going to give me the function back, right? They're inverse operations. That's going to give me the function back. So the function I would get, so what I'm doing now is I'm integrating this derivative here. The antiderivative of 3 with respect to x is 3x. And the antiderivative of 2xy with respect to x is x squared y. But I also have to allow a gy function in the function. Okay, because if I were to take the partial derivative of this function, it would give me 3 plus 2 times xy. It would give me that. It absolutely would. So I'm trying to construct a function f here that's as general as possible. Adding a gy is okay because the derivative of a function of y with respect to x equals 0. So indeed, the partial derivative of this function here, okay, with respect to x equals 3 plus 2xy. So, I'm trying to find out what the function is. Now what I'm going to do, you see, I have to use all the information in the problem. So I've utilized the first equation, but now I got to utilize the second equation, the second partial derivative. What I mean is the partial derivative of f with respect to y. Well, what I can do is this equation 3, I can differentiate that with respect to y. And if I do, I'm going to get then the partial derivative of f with respect to y equals x squared plus g prime of y. That's what I'm going to get. So if why is this nice? Because what I can do is I can compare equation 2 and equation 4. I can compare them. They're both equations for the partial derivative of f with respect to y. And if I can compare them, oh, they're almost the same, but it turns out that this negative 3y squared would have to be equal to g prime of y if equations 2 and 4 are the same equations. So that means negative 3y squared has to equal g prime of y. And therefore, g of y is negative y cubed plus k. Again, we try to be as general as we can. As general as we can. Okay, let me know if you have any. Okay, so now what we can do is, now that we know g of y equals negative y cubed plus k, we can substitute then, we can put that in, we can put this, let me just clear this, we can put this gy function, we can substitute it in here. And that's actually what I have on the next page. That's actually what I have on the next page. Well, no, wait, no, I got it at the bottom, don't I? Here we go. Therefore, this here, f of xy equals 3x, f of xy equals 3x plus x squared y minus y cubed plus k. That's the desired potential function. All right, are there any questions? Are there any questions so far? May I move to the next page? Maybe give me a thumbs up if you're ready to go to the next page. Okay, Christopher is good. John is wonderful. And Ryan, good. Okay, well then let us go to the next page. We've identified our potential function. K, by the way, could be any constant. All right, well now we're going to utilize the fundamental theorem of line integrals. We can do that. We can do that now because we know our potential function f. We know the potential function f. We have a conservative vector field, and we know our potential function f. So the first thing I have to do is compute the endpoints. This particle, we know the path it takes. We know it takes this path. It's given to us. We know it takes that path there. What's the beginning point and what's the end point? Well, at t equals 0, we have the initial point. and at t equals pi, we have the ending point, the terminal point of the path. Okay, let me give you a moment to catch up to here. Okay, so all right, we have that the particle starts at at time zero. At time zero, the particle is at position 1j. Well, you could think of that as 0, 1, right? And at time pi, which is the end time for the particle's position is at negative e to the pi j. Okay, well, you could think of that as just 0 and negative e to the pi. So, by the fundamental theorem of line integrals, the work, right, this integral here, this integral is the work that this force field does in moving the particle from its initial point to its terminal point is equal to the sorry, I'm going to say it the right way. It equals the integral of the vector field gradient, which is the gradient of f. And that's because the vector field f equals the gradient of f, right? So you're just substituting in for vector field f. You're substituting in, hold on, let me phrase this another way. Hold on. So the vector field f is equal to the gradient of a function. So when I compute the work, I can replace this vector field f with the gradient of my function f. And now we use the fundamental theorem of line integrals, and that gets us down here. So I got one more page here, but are we okay? Are we okay up to this? Please let me know if you have any questions before I move to the next page. Okay, maybe give me a thumbs up if we're ready to go to the next page. All right, thank you, Ryan. Thank you, Ryan. Thank you, Robin. Okay, next page. Thank you, Ryan. All right, so now we do the evaluation. Okay, now we do the evaluation. Okay, so remember our function of x and y, let me see, it was equal to 3x plus x squared y minus y cubed plus k. Okay, plus k. I don't know why that line always. Got to be a better way to erase, right? That's all right, we'll get it. There we go. So you can see what I'm doing here. 3x plus x squared y, 3x plus x squared y minus y cubed and you got your x and your y here. Okay. And then I do the same thing for 0 and 1 on this part down here. The k's cancel out. The k's cancel out. And in the end, for the work, you're going to get e to the 3 pi plus 1. I think I had a student maybe a number of years ago actually actually do this problem maybe the old-fashioned way, and it took quite a while to do. I don't remember, but it's very helpful to know this theorem, right? Very helpful. So this means that the force field is actually overall the net work that the force field does in moving the particle along this path in the xy plane is positive because the work's positive. And you could draw the particle on top of the vector field, and you could see that in section 13.2. I have a program that it actually corresponded to example 7, one of the examples we did in our last class. There's a program where I actually have a vector field superimposed on a curve, on a path. So you can always you could verify. I mean, you know what I mean. You could get an intuitive feel if the work's positive, hopefully, based on a graph. And you would just have to adjust the MATLAB program for your vector field and your path. But there we go. So this is much easier than computing the work directly. Much easier than computing the work directly, right? So just a comment, without loss of without loss of generality, you may always let k equal 0 in your potential function. So like in WebAssign, when they want the potential function, well, they have like usually the plus k there, but you don't have to, you could just let k equal 0. But I generally like the k to be there. It's just a personal choice for me. Okay, so let me give you a moment to finish copying that. Okay, are there any questions in general class on this? How many like the fundamental theorem of line integrals? How many are liking that? I think it's a pretty cool theorem. Okay, very good, Ryan. Excellent, excellent. So remember, thank you, Eric. Excellent, excellent. It is interesting, but the fundamental theorem of line integrals works when you have conservative vector fields. Please keep that in mind. If your vector field's not conservative, then you have to compute the work using the technique you learned in section 13.2. Okay, on that note, let me stop the recording.